This video is a demo for EE542 Lab 4 network bandwidth measurement. So in this lab, we will demonstrate on how to measure throughput and bandwidth using the iPerf tool. So to begin, we create an experiment in Deterlab by using this NS file. So we set two nodes A and B, and we connect them using a link of 1 megabits per second bandwidth and 25 milliseconds round trip delay. So once the experiment is created and the visualization is verified, we ping one of the nodes from the other node to verify that the round trip delay is 25 milliseconds. So we first SSH into node A, and then we ping node B. So the IP address of node B is got from the details tab. So the IP address of node B is 10.1.1.2. So we ping node B. So we see that the round trip delay is around 24 milliseconds, which is desired. So once this is verified, uh, next step is to verify the bandwidth in the link is 1 megabits per second. So to do this, we use the iperf tool. So first we go into the iperf directory that is here. We do the same thing in node B as well. So once we go into the iperf directory, so we can run the iperf tool. So to run, one of the nodes will act as a client and the other node will act as a server. So in my case, I have taken node A to act as a server. So running the server iperf here. So the command line arguments are -s to show that it is a server. Uh, Now you can see that the server is listening on the TCP port 5001, and the default TCP window size is around 85.3 kilobytes. So we move to node B, where it acts as a client. So the command line arguments for the client is -c followed by the IP address of the server, which is 10.1.1.3. So once you run this, you can see that the client is connecting to the node A in this connecting to the same port, and the default window size is 85. Wait for the report from the server, and we see that the bandwidth is around 1.65 megabits per second. So once this is done, we also need to calculate the bandwidth in UDP mode. So by default, the iperf is calculated in TCP mode. To shift over to UDP mode, we just add another command line argument called -cu. So now you see that the server is listening on UDP port 5001, and the default UDP buffer size is around 208 kilobytes. So we do the same thing on the client side. So we add -u. So we wait for the server report to come back, and so we see that the bandwidth across the link is 974 kilobits per second. So once this is done, the next step is to repeat the same procedure, but with the link the set to 10 and 100 megabits per second. So to set the link without swapping the experiment out, we can go into modify traffic shaping and set the bandwidth to whatever we desire. So in this case, 10 megabits per second will be 10,000 kilobits. So once this is done, we click execute. So now the link will be set to 10 megabits per second. So after this, the same procedure is repeated, and we see that for 10 megabits per second in TCP mode, the throughput was around 9.39 megabits per second, and with the link set to 100 megabits per second, the throughput was around 94.5 megabits per second. And in case of UDP, since iperf limits the bandwidth to 1 megabits per second, we'll have to add another command line argument called -b followed by the desired bandwidth, which is 10 megabits. So once this is run, we see that the throughput was 10 megabits per second, and when the link bandwidth was 100 megabits per second, the throughput was 95.7 megabits per second. The next step is to increase the maximum window size in TCP. So this is done by typing in this command in the command terminal. So after this, the throughput is calculated for varying window sizes. So to vary the window size, the -w option is used. So while passing the command in iperf, along with the other command line arguments, the -w option is used, followed by the window size, that is 64K, 128K, and 256K. So once this is done, we see the various TCP throughput obtained for various window sizes. So for 64 kilobytes, the throughput was obtained to be around 19 megabits per second. For 128 kilobytes, the throughput was 38.6 megabits per second. And for 256 kilobytes, the throughput was 78.8 megabits per second. So we see that as the window size increases, the throughput also increases. This is because of the formula throughput is directly proportional to the window size. Since the RTT was kept constant, as the window size increased, the throughput was increased. The formula is given by throughput equal to window size by RTT. So the next question was to run the experiment at 100 megabits per second and 25 millisecond of delay. So putting these values in this formula, the optimal window size was found to be around 312.5 kilobytes. So with this value set, the experiment, the iperf was run and the bandwidth was evaluated. So the bandwidth evaluated was found to be around 85 megabits per second. The value obtained was still less than the optimal bandwidth, that is 100 megabits. The reason was because of the saturation attained in the network and also the TCP overhead. These were the reasons for the throughput to be less than the optimal throughput.
Hello, in this video I'll be doing the demo of Laboratory 4 section 1.2, that is gigabit links. In this lab we have to create an experiment with two nodes connected by a gigabit LAN. So let's go ahead and see how to do that. So in Deterlab we begin an experiment and give the name as lab 4 network bandwidth management tool and description as gigabit links, and choose an NS file. I'll go over the details later. And then ideal swap is changed to 1 and swap in immediately and click submit. This will create an experiment named NBM2. I've already done that, so I'll go ahead and show how it is. So once the experiment is successful and is swapped in, we see it like this. The NS file contents is basically to create two nodes, and as instructed to set a LAN link between the two nodes with 1 gigabit data rate and 0 millisecond delay, and both of them will run Ubuntu 16.04. And the next step is to use ping to determine the average RTT between the two computers. So I've already done that. So here we can see that we ping using the IP address which is obtained from the details tab of the two nodes, this and this. So we use the ping and the IP address, we get the average RTT to be 0.152 millisecond. The next step is to find the bandwidth delay product for this link. We know that the link is 1 gigabit and the delay is RTT is 0.152, so this gives us a bandwidth delay product of 152 kbps. The next step is to use iperf in UDP and TCP to measure the bandwidth and throughput respectively. So this is what we do. We run the command using /mlab iperf -c as a client and the IP address of the server we want to connect, and /mlab iperf -s as a server. If you have to run it on UDP mode, we use -u in the command line. So here we can see that the throughput is 943 megabits per second, and for UDP it is 327. So we tabulate and we notice that TCP has higher throughput than UDP, since UDP is a non-reliable protocol. And to get an optimal bandwidth for UDP, we go on increasing the bandwidth towards the link speed, and we notice the rate at which there was no packet loss. So this was found to be 325 megabits. So at this point there was maximum bandwidth and no packet loss. Next, if we leave send or receive windows at the default, we see that the link performs well in UDP, in TCP, but UDP it's 327 megabits, which is less. The next step is to vary the window size in TCP and see the effect on the throughput. So we go ahead and do that. So we see that 85 kilobyte is the default window size where we have optimal bandwidth, and then we vary the window sizes to 64, 128 and 256 kilobytes respectively. We see that the throughput is fairly constant, and when the window size is more or equal to the bandwidth delay product, we get the optimal throughput. Next step is to see if we set the send or receive window to too small, what is the throughput again. So we set the window size to 16 kilobyte and 32 kilobyte to experiment. We see that the throughput is very less, around 356 and 526. Next is in the gigabit link. Initially we did the experiment with 0 millisecond. So here we tend to give 1 millisecond and 5 millisecond. Deterlab doesn't take 1 millisecond in the NS file, so we experiment with 2 and 5 millisecond and we see the effect of it. So with 2 millisecond we see that with the default window size it has a maximum throughput, and for 64 and 128 and 256 it goes on increasing as the window size increases. Similarly for 5 milliseconds the behavior is the same, except that if you see, for example, for window size 64 the throughput is 47.2 for 5 millisecond, and for 2 millisecond it is 111. So it decreases as the delay increases. So this section basically is the end of gigabit links, and from the section we saw that how window size affects the TCP throughput and the UDP bandwidth. Also, if we can scale only the window sizes and not touch the delay, and see how the throughput varies. So this is it. Thank you.
The third part of the program deals with the secure copy program. Here they have asked us to create a 100 Mbps link between two nodes and set up some initial delay between them. So this is the NS file for the same. As you can see, there are two nodes, node A and node B. A full duplex link of 100 Mbps with an initial delay of 5 milliseconds is set up between the nodes, and both node A and node B are loaded with Ubuntu 16.04. This is a visualization for the same. So there's node A and node B, and here it shows that there's a 5 millisecond delay between them. This delay is then later reduced during the experiment. These are the details of the experiment. The qualified name for node A and node B is provided to us, and this is used to SSH to node A and node B. The next part of the experiment asks us to calculate the RTT between node A and node B when the delay is 0 millisecond. So from node A we ping node B with using the IP address provided, and we can see that an average delay of 0.5 millisecond is obtained. We then have to calculate the bandwidth delay product. This is done by multiplying the bandwidth, which is 100 Mbps, with the delay which we obtain, and we get an answer which is 50 kilobits. The experiment is then again repeated with delay set to 5 millisecond. This is done by changing the modify experiment parameters option in the Deterlab, and once that is done, the delay is set to 5 millisecond, and the bandwidth delay product is calculated to be 103 kilobits because the delay is obtained to be 10.3 millisecond. The question then asks us to create and mount a temporary file on each node, that is node A and node B, and to create a 200 MB file on node A. So the command sudo, which is super user do and make extra file system on the directory \mount is used to create an extra file system. So this is executed on node A as sudo user testbed bin make extra fs on the directory \mount. So this command makes the file system, mounts it on the directory mentioned, and it also makes an entry in \etc fstab, which can be used for future referencing of the file system. So this command makes use of the free space which is available to the user from the root disk. The same command is then carried out on node B, and we can see that the mount \mount is created, and there's a make directory which is \mnt \local, and the entry is also made into /etc/fstab. When you run an ls command on node A, we can see that the local and lost and found are the two folders which are present under node A in \mnt. Next we run the command cd \mnt and dd, which is data duplicator, and this is the syntax for the data duplicator command. So the data duplicator command is used to create a 200 MB file. The input and the output for the data duplicator program is given here. Here we can see that the input is taken from \dev /u random, and the output is stored as in data.bin, and the count is 200, that is 200 MB of data is created. The question then asks us to SCP from node A to node B, and this is the format for SCP which is given, and this was carried out in the experiment. So here we're running scp data.bin, which is a file which is present in node A, and it is being sent to usc542cr, which is the username for the project which we are accessing, and this is at node B, and it should be stored in \mnt folder directory. So this is the scp command. It shows that the 100% of the data.bin file was transferred, which was a total of 200 MB, and the throughput obtained was 11.1 Mbps, and it took 18 seconds to do the same. Once we run an ls command on node B, we can see that data.bin has been transferred to the node B from node A. The next part of the experiment asks us to experiment with different delays and see how the RTT is affected. So while running the same program on Deterlab, we changed the RTT from 0 to 5 to 10 to 30 and 50 milliseconds, and we noticed that there was not much change in the throughput, and it remained a constant of 11.1 Mbps throughout the same. The next part of the experiment asks us to try the same by changing the packet loss parameters. So the packet loss parameter had to be changed from 0.1% to 5%. When this was carried out, we noticed that for the initial few parameters, when we varied it from 0.1 to 0.25, there was not much change in the throughput. It remained around 11 Mbps. So as you can see, it was 11.1 and 10.5 was the variation we obtained. And then we increased the parameter to a higher extent. we increased it to 3% and obtained throughput for about around 10 Mbps. And when it was further increased to 3.5%, it was around 8.829 Mbps. And when it was changed to 4% and 5%, it was around 8.5 and around 7 Mbps in total. This was plotted onto a graph. As you can see, throughput is mentioned here, and it's been between 0 and a maximum of 12, and the packet loss was varied from between 0 and 5, and this is the graph we obtained for the throughput. The last part of the experiment asks us if we can access a server in Switzerland and to calculate the delay for the same, and if a person had to access files at CERN and had to SCP to it, will it be possible? So we tried to ping a random server, which was a DNS server in Switzerland, and we obtained a delay of about 225.25 milliseconds. And as long as the person knows the details for the remote access at CERN, we can SCP to it, because SCP works over SSH and SSH requires authentication.